Yes.
Yes.
Okay. Yeah, hi everyone. How are you all?
Good evening.
Yeah, fine.
Good evening. Yeah, done. So in the last session, we have discussed till I2C protocol, right? So do you have any doubts still here? Till I2C. We already did the
No, as
verification
such.
using system Verilog and also have shared the code to all. So any till verification, is it clear now?
It's clear now.
Yes.
So protocol, okay, specification of APB protocol. Tomorrow we'll see on verification part, okay, system Verilog verification, and if time is sufficient, tomorrow we can complete APB, or else we can extend to next week. Okay, mostly next week we are going to start AHB protocol. For AHB protocol, 1 or 1.5 week, and after AHB protocol, we are going to design AHB to APB bridge. Okay, actually AHB to APB bridge is not included in this, but I want to discuss the bridge also. Okay, and next we will discuss on AXI protocol. Not AXI Lite. We will discuss total AXI protocol with the major features. Okay, we'll see what are the differences between AXI Lite and AXI protocol and how it will be working. Okay, so that you will get overall idea, and also hands-on sessions we are going to discuss, right? We are going to implement the design and also verification. APB protocol in system Verilog verification. Already we have seen one I2C protocol verification in system Verilog. So APB in system Verilog, AHB and AXI is in UVM. AHB we are going to design RTL and also verification in UVM. For AXI, we are going to develop the VIP UVC. Okay, so this is what next 5 to 6 weeks schedule. Okay, in the
VIP.
VIP in the sense, see, whenever we want to design some IPs or VIPs or whatever, design from the RTL. Okay, we generally we buy from the vendors. There are a lot of IP vendors in industry, so we will buy from that. VIP in the sense, where we have both UVC and also RTL design. We don't have. We just have the UVC component. Okay.
Yes.
So first of all, we'll discuss on introduction to AMBA protocols, and then APB. APB and AHB are not in IP. Just it is like normal verification. For AXI, we will discuss IP level. IP level in the sense it is a predefined block where we can reuse anywhere, just plug and play manner. Okay. Generally, in industry, we don't buy, we don't design all these components or whatever the protocols. We just buy from the vendors. Like that, IP is nothing but where we can directly pre-design. It is a pre-designed and also pre-verified some reusable block. So coming to the AMBA protocols, coming to the classification of AMBA, it's a advanced AMBA means it's an advanced microcontroller developed by ARM.
Your voice is
Because
breaking. sometimes.
And also subsystems, right? So can you tell me what is the difference between IP subsystem and SoC, system on chip? What is the difference?
For system on chips, we use different IPs. Like we use pre-verified IPs for SoC, which we can buy from different vendors. IPs can be bought from different vendors, and we connect them and just verify the whole data file.
Okay, so in a system on chip design, whatever SoC, there will be multiple number of sub blocks, subsystems we can call. Okay, so core related or processor related, there will be one subsystem, graphic processor related one subsystem, some image processing related or memory related one subsystem, and any external devices which are connected or internal small bandwidth devices will be there, right? Low peripheral devices all comes under one type of subsystem. So nowadays mostly AI technology is involving. So especially for that we have some image processing techniques and ML and AI techniques will be there, and also those are included in the separate subsystems. So all will be in a one subsystem which are related to AI. So these we call as a subsystem. Within the subsystem there will be small blocks, because memory, in the sense memory is just like a subsystem, but within a memory we have lot of different types of memories, like DDR memory will be there, or some controllers will be there, DDR DMA controllers will be there, RAM ROM memory will be there, 5 connections will be there. So within a SoC or within a subsystem there will be multiple number of IPs. Okay, so now within this is what top level we call it as a SoC. To intercommunicate, so to processor will communicate every block of the chip, right? Every signal, whether it's a small signal or just internal signal or top level signal, whatever, the processor will communicate to every signal, okay, bottom to top. So here we have a interconnect. Mostly processors will work at a high speed, right? Very high speed. Low speed peripherals like keyboard or mouse pointer, which are externally connected, and internally connected like a Bluetooth or Wi-Fi module or GSM module or any fuse. Okay, these all are internally connected, which are low power devices, or which are low power functional blocks that works at a low frequencies. Okay, so processor every time it will be communicating at a high speed only. It nearly 256 hertz, 256 gigahertz, not hertz, in terms of gigahertz. Okay, so processor will work at a very high speed frequency. So every subsystem will be connected to this interconnect. Okay, so this red color one is a interconnect top level, and inside each subsystem also there will be some interconnects which are parallel communication like this.
Hello?
So
Hello, we
via
can record this
the,
session. We can record this session.
already it is recording.
Okay.
Already it
recording.
is recording. Okay, see, here we need to communicate subsystem to subsystem. Okay, so for that purpose we are using interconnects. Okay, these interconnects are nothing but bus signals or bus connections we can call. Okay, so processor related we have some types of interconnects, non-cores related some type of interconnects which is differ from coherent, non-coherent, that is separate concept. Okay, so whenever we are trying to send some data or trying to communicate within the chip, we need to follow certain rules. Okay, because processor works at high speed, some features, some high level features will be there where it generate multiple number of instructions. We need to work with multiple tasking at a time in fraction of seconds, and memory is for storing purpose. Okay, and like the different peripherals have its own task. Okay, so whenever we are transferring the data, whenever the handshake between one subsystem and another subsystem happen, we need to follow some rules. Okay, so for that purpose we divided n number of protocols. Okay, so here first thing is interconnect. For interconnect or for bus communication or parallel communication, we are using AMBA protocols. For bus connection, which are parallel communication. Okay, these all are AMBA protocols. Before we have seen UART, I2C. UART and I2C SPI also serial communication, but UART is a communication for external device. Okay, where USB connection, we are using USB ports to connect to mobile phone or to connect some external device like a printer, scanner, or some joystick. Okay, and internal serial communication devices like I2C. We already seen the applications for I2C protocol, right? A microcontroller to different types of sensors within a mission. Suppose there is a washing machine. In washing machine, there will be two types of controllers. So how the microcontrollers are communicating with each sensors? We have seen the example. So that is I2C protocol. Within a chip, need to communicate. That is that to slow communication, not at very high frequencies. Okay, so like that, in AMBA protocols, we have high speed protocols and low speed protocols. Okay, coming to the high speed protocols, we call as a AXI and AHP protocol. AXI, AHP protocols are communicate with the processors, memories, controllers, and graphic processors, high-speed devices, whatever we connect within the chip. AXI is used to connect with these components. Okay, and for low-speed peripheral devices, we use APB protocol. APB for timers, mouse pointers, keyboards, or some any Bluetooth devices or Wi-Fi module or GSM module or Pi interconnects. Like this very small frequency devices will use APB protocol. Okay, so now you will get a doubt. So here processor is communicating with the suppose Wi-Fi module. Okay, Wi-Fi module is a very low speed communication. Processor works at a high speed. So low speed to high speed, every time if you see, we need to make a bridge between both. Otherwise, we will have the data loss. Data lossage is one of the major thing if there is a frequency mismatch, right? We have seen a lot of examples even in your I2C and also in UVM while we are writing the program from generator to driver. If there is a frequency mismatch, the data lossage will be there. So for that purpose, we need to check. Okay, between transmitter to receiver. In the same way, here processor is working at a high speed and these peripherals working at a low speed without any data lossage. To make the synchronization between each other, here we are using a bridge. Okay, so that's why AXI data will be converted to APB. APB data will be converted to AXI through this bridge, whatever it's a, whether it's a AHB or APB, whatever. The bridge is used to communication between two high speed to low speed. Okay, you may think like what is the use of that? Like you may think, suppose here processor is working at a 256-bit data. Okay, so 256-bit data, it can be processed at same time. Okay, within just 2 seconds or 5 seconds. But here, these small devices can accept only 32-bit data. They are running at a 32-bit data or 64-bit data. Okay, so if there is no synchronization between these two, here processor is sending some 256 data, but here APB whatever APB protocol or any peripheral cannot accept the 256 data. Okay, so what will happen there? Data loss. So whatever the processor is sending, total data, receiver side, it cannot accept all the data at a time, in single time. Okay, so for that purpose, what we are doing here, AXI to APB, we are constructing one bridge. Okay, so whatever the 256 data is there, that data will be divided into half parts, like 64-bit, 64-bit, 64-bit. So by using APB protocol, we can accept till 250 till 64-bit suppose. Okay, so this is how we communicate the data between processor to sub devices using the AXI, APB, AHB interconnect. Okay, another thing, we have seen your I2C SPI, those all are serial communication protocol, bit by bit, one by one bit will be transmitted. But here all are parallel communication, bus connections or interconnects. Okay, so all are parallel communication data. Within parallel communication also, we need to check the what is the size, what is the capacity, what is the bandwidth, the frequency. By taking all these measurements, whatever we have divided into APB, AHB, AXI protocols. Okay, did you got the point, everyone? Overall idea?
Yes.
Yes, ma'am.
Okay, so how much do you think like a frequency differences between AXI, APB and AHB? Maybe it's a latest version or ongoing version or oldest version, whatever. So what will be the basic typical frequency? No idea? Okay, so mostly APB protocol works under, these are some of interview questions you will get. Suddenly maybe we'll take it as a, like, we won't get those questions, we'll think like that, but suddenly if they ask the question, we need to answer, right? So APB protocol works at 25 to 50 megahertz range. Okay, so mostly we will connect a slow peripheral devices like any IO device, GPIO or UART or timers. These type of small peripheral devices we will connect 25 to 50 hertz, megahertz. And coming to AHB protocol, 100 megahertz to 250 megahertz variable. Okay, it is a medium performance, medium to high performance compared to AXI. Mostly for here these system level on-chip communication, and for system level data transfer we use AHB protocol. Okay, and coming to AXI protocol, it up to 1 gigahertz and more than that. Okay, always it will be in a gigahertz only, not in a megahertz or even hertz we don't use anywhere. So it is a very high performance, mostly used for register transfer. AXI protocols are used for register transfer, high speed data transfer, and memory interfaces purpose and multi-core processor purpose. Okay, AXI protocol nowadays, whatever the processors we are using, multi-chiplet or mono-chiplet SoCs, whatever we are using, AXI only, but with advanced features. Okay, we will discuss what will be the advanced features for all protocols. So from AMBA 1, 2, 3, 4, 5. So what will be the advanced features we will discuss now. Okay, till now, is it clear?
Yes, ma'am.
Yes.
Yes, ma'am.
Yes.
Ma'am, you are not audible.
APB protocol comes under AMBA 2 and AMBA 1.0 also, but mostly we call it as a AMBA 2. It is a APB 2. Parallelly, we call it as a AHB. Okay, so AHB means, APB means advanced peripheral bus. AHB means advanced high performance bus. Okay, concept, and it is also worked with a very low bandwidth. Okay, compared to AHB. In AHB also we don't have the pipeline. We have pipeline and non-pipeline, both are available. But in AXA fully pipelined. Okay, and in APB protocol we don't have the burst transfers. Burst transfer in the sense, suppose in APB protocol we are transfer data in
Prashanti, your voice is
data.
breaking many times. It's not audible very clearly.
Yeah. You rejoin.
Okay, okay, wait. Am I audible now?
Yes, ma'am.
Okay. We'll see for 10 minutes. If it is not audible, tomorrow I can continue morning and evening session. Okay, see. So compared to the APB protocol, in AHB protocol, we have some advanced features like a bus transfers and aligned, non-aligned increment wrapper. In the sense, it is introduced into
Ma'am, your voice is breaking again.
mostly.
Yeah, it's breaking. It's breaking. It's stopping for a while and again we are able to hear. It's pausing for like 2-3 seconds or 5 seconds and again. Yeah.
Actually, today internet is not good. Hello.
Yes, audible.
Okay, fine. So coming to the AMBER 3, we have different types of subversions like APB3 and AHB Lite and AXI3, mostly focused on AXI. Okay, AXI3. Whatever the features are there in AHB protocol, we are taking some advanced features in AXI It supports the bus transfers, multiple out of order transactions, and it have separate addresses and separate data phases. In a AHB protocol, we have address phase and data phase separately. But in AXI protocol, we have channels which are more advanced and also unaligned data we can send. Unaligned in the sense, in AHB protocol, we send the data in a particular
Again, your voice
or
is
wrap
breaking down.
or delete. Is it same for all?
Yes.
Oh, yes.
Yes.
It's breaking.
Okay. I can continue tomorrow morning and tomorrow evening, 2 sessions in that case.
Ma'am, please try again if it's possible now. You will continue today only.
If it is audible properly,
No, actually your voice is breaking between for like 3-4 seconds, and then there is no continuation actually.
okay. Am I audible now?
Yes, audible.
Okay. 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 I think now you won't get this problem. Okay, see. AMBA 3. In AMBA 3, we have APB 3 and AHB light version and also AXI 3. Okay. And in this AXI 3, we have the features like out of order transaction. We will discuss one by one very clearly whenever we move to the each protocol. In AXI, we are going to cover the special features of out of order transactions, 5 different channels and multiple order transactions and burst transfers and also aligned, unaligned data, wrap, increment, all these things we are going to cover in AXI. Okay. And next, AXI 4, I mean AMBA 4. In AMBA 4, we have different enhancements to the AXI. Like AXI 4, we call AXI 4 Lite and AXI 4 Stream also. Actually, in this AMBA 4, the cache coherent interconnect has introduced. Okay, cache coherent interconnect in the sense before I have told, right? For processors, we connect one type of interconnect. For non-core, we connect one type of interconnect. Okay, we have coherent interconnect and non-coherent interconnect. Okay, so wherever we have the core related, there we have the cache interconnect. That concept is involved in this AMBA 4 cache coherent interconnect. I will give you the brief introduction to that also, the concept. And also AXI 4 are used to map the memory mapping purpose and also used for high interconnect, high performance interconnects. Okay, AXI 4 is a very simple, just for control register purpose only, not like a AXI. light is different and stream also different. Stream also some more little advanced. It just work for high speed unidirectional data streaming, but not like a AMBA. AXI. AXI is totally having different features, whatever we discussed before, and also cache coherent interconnect is involved in this. And AMBA 5. In AMBA 5, CHI has introduced coherent hub interface. Before ACE means it's a coherent interconnect, but CHI means hub interface. Hub interface means where we can connect the cache coherency in multi-processor systems. Multi-processor systems means where we have the integrated graphic processor and the normal central processing unit with n number of cores. In that we have the multi-chiplet or monolithic, where we have the CCD and IOD configurations. So CCD in the sense core related, IOD in the sense input output devices related. Okay, both are having in a same SoC. That's what we calling as a multi-chiplet. One side is a CCD die, another one is a IOD die. Actually, not processor having only one die. In one die, we have the total SoC, system on chip design. But nowadays, mostly in the AMD processor, whatever we are using last 24 from Ryzen processor, we are using the multi-chiplet. Multi-chiplet means we have two dies. One is a CCD related die, one is a IOD related die. I will just show you the concept. If you are interested, just go through that. See, AMD EPYC processor, CCD core complex die, and IOD input output die. In mostly we use CCX concept, and here CCD will be divided into n number of CCX. CCX in the sense n number of core. Core 1, core 2, core 3, core 4. And remaining is divided as a IOD. IOD in the sense it have memory controllers and Infinity Fabric die-to-die system management unit. For every IP, we will connect a system management unit. Where every data will be sent. Suppose here from core to memory controller, the data will be sent through the system management unit only. Like this second CCX to USB, the data is sending through SMU only. Okay, so DDR4 are the memories, and this is how the IOD 2x CCD and also 1x IOD. This is how we connect. We call it as a multi-chiplet. Monolithic means you won't having this CCX. See here, monolithic chip and chiplets. What is the difference? Means monolithic means a singular piece of silicon constructed as a unit. Chiplets means where the devices like graphic processor. Nowadays everything we are getting integrated graphic processors, right? So like that, where graphic processors will be integrated on single chip. Okay, just refer some data. So for that purpose, mostly these coherent hub interfaces are used. Multi-processor systems. Multi-processor systems means whatever I have shown you, the CCD will be divided into number of CCX, where each CCX we have number of cores. So it is optimized, and also very data intensive processing is also very high, and mostly suitable for system on chip designs like mobile devices or server processors. We use AMBA 5. Okay, so these are the classification of AMBA 2, 3, 4, 5. Okay, So coming to the APB protocol, what is meant by APB? APB in the sense it is a low power, low bandwidth, mostly used for small components like peripherals, timers, UARTs, GPIO like that. And it's a non-pipeline and no burst transfers. Okay. AHB protocol, single master, multiple slaves, and it is connected for high bandwidth and pipelined. And it have the best features called what we are going to discuss the features in the sense burst transfers, split and retry response, that is also one of the best feature, single clock edge operation, wider data bus, it also having wider data bus up to 64 128 bits we can connect using the AHB protocol. Okay, in the same way AXI having channels. AHB have only phases, address phase and data phase, but AXI having the channels. Channel in the sense where we can communicate all the data parallelly. We no need to wait. There are no dependent signals. That means APB. Suppose if you consider APB, whenever write operation is going, whenever we do the write operation, we can't do the read operation. Okay, whenever we do the read operation, we can't do the write operation. Both are interdependent. In AHB protocol also same, but in AXI protocol we have the channels, write channel, read channel. Both are independent. Independent in the sense if you want to write the data, you can write the data parallelly. If you want to read the data, you can read the data. Okay, so both are interdependent, independent. Like that, we have out of order transaction, multiple order transaction. It works at a high speed and separate control parts and data parts, flexible bus transfers. So mostly in AHB also we have the bus transfer, but in AXI with the more advanced features, and also we have quality of service signaling. That means how the data has transferred. We can check how the signal issues are getting or not, and also it support the memory mapping. That is, these all are for AXI features. AXI 4 also will be there. I already told, just for simple control registers and others. Okay, so today we will complete APB protocol. I think everyone got clarity on APB protocol. So any doubts still here?
No doubt.
Okay, fine. So coming to the APB, advanced peripheral bus protocol. Okay, so coming to the features, very simple protocol. Just you can learn within 1 or 2 days. Very simple protocol, and there will be very less number of signals. Just 20 to 25 signals will be there. But if you go with just a second. But if you go with AXI protocol, in each channel only we have nearly 50 signals. Like that we have 5 channels. Write address, write data, read address, read data, response channel. Like that in each channel we have 50 signals nearly. But in APB protocol, overall protocol, we have only 25 signals. So that's why we are calling it as a very simple protocol and easy to implement. And it's a low power protocol. It doesn't have any complex logic, or it works at a very low frequency. I already told, right? Nearly 25 megahertz frequencies. It will work 25 to 50 megahertz, and also very low cost, non-pipelined. That is one of the limitation, non-pipeline. That means we need to use a single cycle transfer, and it is peripheral.
Pipeline and non-pipeline means.
Pipeline and non-pipeline means, suppose I will tell you in processor related. pipeline means what? Suppose there are 5 number of instructions. Okay, 5 number of instructions you need to send one by one, one after another one. So if it is a non-pipeline, first you transferred one instruction, and after sending this instruction, after sending this instruction, that means after 5 nanoseconds, second instruction you are initiating. That means for second transaction also it is taking 5 nanoseconds, and next third instruction another 5 nanoseconds, and fourth instruction another 5 nanoseconds, and fifth instruction another 5 nanoseconds. That means you are waiting one by one until it uh, uh, transferred. Okay, but if you go to pipeline, suppose first one is transferring, first instruction is transferring. Here we will divide the instruction into some steps or into some parts we can call. That means we have some stages: fetch, decode, execute, memory, write, and register, write back stage, whatever. Okay, so in these 5 stages, one instruction will be completed. Okay, so in this case, in first case, what is happening? First instruction, fetch. It should complete fetch, decode, execute, write back, and memory write stage. These 5 stages completed, then second one is going. And after second one, all stages are completed, then third one, and third one also completed all 5, then fourth one. Okay, but pipeline means suppose first instruction is in fetch stage. Okay, and next it going to decode stage. Okay, whenever first instruction is in decode stage, second instruction is starting, initiating, it is ready to send. Okay, whenever it is in decode stage, and first instruction is in fetch execute stage, then second instruction is in decode stage, parallelly third instruction is in fetch stage. Okay, what is this fetch, decode, execute, all these things means, suppose in a processor, if you see, fetch is nothing but you are taking one instruction, the memory, from the memory one instruction you are taking. So instruction means what? Basically we write in a assembly language programming, right? Add odd 1 comma or 2 comma or 3, sub or 1 comma or 2 or 3, or any logical operations like that we write in a assembly language program. But that is a human understandable program, but processor doesn't understand that whatever coding is there, it doesn't understand. We need to decode that. Decode in the sense, however our numbers or characters are decoded into the binary values or encoded into the binary values, in the same way this instruction should decode into the processor language. Okay, so that's why decoding and then executing, whatever the instruction we are getting, that it should be executed in this execute stage, and memory write stage, write back stage. That is how we divided execution part. Okay, so to execute this, it is taking some time, 5 seconds. Here within 5 seconds we are allowing second transfer, second instruction, at the same time third instruction. Whenever first one is in write back stage or memory state, second one is in fetch state or execute state, third one is decode stage, fourth one is fetch stage. Okay, so if you see, all are going parallelly in the sense pipeline manner. It is not waiting until first one is completed. If it is waiting until first one is completed, the second one should be start here at this point of time. But instead of that, second one is already completed 3 stages, right? Instead of starting at here, already completed 3 stages. So third one also completed 2 stages, fourth one also completed 1 stage. Okay, so that we can reduce the time, total time we can reduce. Suppose here 5 plus 5 10, 10 plus 5 15, 20 25, suppose 25 time unit it took to complete 5 instructions. Here within 10 seconds only we can complete the transfer. We can complete the instruction, whatever the transfer. If you see, if you talk in protocol wise, we can complete within 10 seconds. Okay, so that is a pipeline. In APB protocol we don't have a pipeline. Pipeline in the sense, if you talk in terms of protocol, First we are transferring 32-bit data. Okay, after reaching from master to slave, this 32-bit data, then only we can initiate next transfer, second transfer. Next, after completing this second transfer, only third transfer can be initiated. Okay, so this is what non-pipelined. But pipeline in the sense, parallelly, whatever number of transfers are there, if there are 10 transfers or 15 transfers, whatever we can send parallelly. That's what pipeline. Okay.
Okay, ma'am.
Next, pipeline in APB protocol, we don't have a pipeline, and it have separate read write. I told before, right? Independent, both read and write are dependent. If read is happening, write can't be done. If write is happening, read can't be done. Like that, it have the address data and control signals, and also it supports the wait states, and it is a plug and play manner. Okay, so we'll look into the AMBA APB protocol specification. Suppose if you want to implement something, we must have it's a functional block and all, right? So what is the functional block diagram for APB protocol? We'll see today, and tomorrow session we will implement the RTL design and also verification. Okay, so this is what typical AMBA system. In a SOC, which side we will connect the high speed protocol like AHB or XI, and which side we will connect the low speed protocol. Okay, so if you see left hand side, the blocks, one is a high performance ARM processor, another side high bandwidth on chip RAM, and external memory which is a high bandwidth, and DMA, direct memory access controller, bus master. These all are high speed or high bandwidth or high performance, whatever. So these side we have connected AHB or AXI. ASB we don't use. Okay, AHB or AXI we will connect. And if you see right side, your timer, keypad, peripheral, IO peripheral. So right side all are low speed devices. Okay, that here for interconnections we used APB protocol. Okay, so what is the use of bridge? Without any data loss, we are connecting from high speed to low speed. Okay, so that high speed data will be converted to the low speed data. And also I told in AXI we have n number of channels, 5 channels, and each channel it have nearly 50 number of signals will be there. So how it will be communicated with these, how that data will be converted to the APB means bridge. You will be learning bridge also, the functionality, overall functionality, so you will get the clarity. Okay, so coming to the introduction to APB, all these things I already discussed, like APB stands for Advanced Peripheral Bus AMBA protocol. It's a family of AMBA protocol and mainly used for general purpose register based peripherals such as timers, interrupt controllers, yacht, IO ports, etc., and optimized for minimal power consumption and reduced interface complexity. And it's a non-pipeline protocol, and it transfer, see here, every transfer takes at least two cycles at least. That means setup phase and access phase to transfer one single data. And next, APB interfaces to any peripherals that are low bandwidth. Whatever the low bandwidth peripheral devices are there, to any device it will be connecting. It is connected to the system bus via bridge. Helps reduce system power consumption. It is also easy to interface and also provide the low cost interface that is optimized for minimal power consumption and reduced complexity. Okay, so APB can interface with the AHB and AXI. So this is what overview of APB protocol. Everyone clear? Any doubts? Any doubts still here?
No, ma'am.
Fine. So what we need to concentrate in APB protocol. After this session, I will share you the interview questions also. Mostly how the APB will be connected in a SOC level, like basic operations, and how the signal connections will be there. I will share the interview questions on that, and I will tell you where we need to focus mostly. Okay, before that, everyone try to learn specification perfectly. Okay, so if you go through the specification perfectly, specification is nothing but what are the signals, what is the functionality of APB protocol. If you know that thing very well, you can write the program easily, and whatever the interview questions are getting, you can answer the interview questions easily. Okay. So coming to the signals in APB protocol. First of all, clock. P clock. So if you observe here, P clock, P reset, P address, P protect, P select, all are denoted with the P, is nothing but APB. AHB means H. We will have H clock, H reset, H address, H protect, like that. Okay, all signals will be prefix we have H. Like that. AXI we have different channels. Based on the channels, there will be some prefix. Okay, based on 5 different channels: read side, write side, and responses side, B response or response, whatever. Okay, so coming to APB, first of all, clock. You already know what is the use of clock. For synchronization purpose, every digital circuit we use the clock and reset. Reset is also active low reset. That means whenever reset n is equal to 0, then we can do the reset, or else when reset is high, not on state, just we do the functionality. Next, P address. P address is nothing but where we store the address. Okay, just it represent the 32-bit address. P address in the sense address bus, 32-bit address bus. And P protect. P protect in the sense it's a protection signal. Protection in the sense this signal indicate the normal, privileged, or secured level of transactions where we can access the data. So if you want to access the data, you can put as a normal. Suppose if you are giving some access to the another team, suppose in industry there will be a number of teams, right? So access will be given to one team to another team, and also your test cases, who can access your test cases related to the APB signals, the data. So these all are protected. So this protect signal will be indicate normal, privileged, or secure protection levels. Okay. Next, selector. Select in the sense you already know APB protocol is a single master, multiple slaves. So we can select any of the slave selection. If there are 3 number of slaves, then P select 1, P select 2, P select 3. Like that, 3 number of slaves we can select. Okay. Like that, P enable. Enable in the sense whenever the enable is high, the data can be transferred, or else no. Okay. P write. Write in the sense based on the P write signal only we can do the write operation or read operation, because only we have one signal. Okay. In AXI, as I told, we can do parallelly. Both are independent. Okay. But here both are dependent. If write is high, then we can do the write operation. If write is 0, then we can do the read operation, like that. Okay. Next, write data. We need to write the data. Okay, write data in the sense whatever the data you want to send from master to slave, that will be the write data. Slave to master will be the read data. Okay. Next, strobe signal. Strobe signal is nothing but it indicates which lane we need to pass the data. P strobe, right strobes we call. Okay, strobe signal in the sense just it indicates which lane, like PCIe, if you see, we have n number of lanes, lane 1, lane 2, lane 3. In each lane, we pass 32-bit data or 16-bit data or 8-bit data in each lane. In the same way, just we will connect the transaction in a strobe. Okay, but in APB protocol, we don't have the strobe signal directly. In AXI protocol, we have the strobe signal. W strobe we have in AXI directly, but not in a APB. Okay. Next, sorry. Next, P read data. Or data is nothing but read data, and SLVE or is nothing but slave error. P slave error. That means if slave is doesn't get the proper data, if any errors are there, it indicate the slave error signal. Okay, so that we can understand the data has not reached properly. Okay, so whenever the transfer has failed, it will be enabled. Okay, slave cannot, whenever the slave is not responded, or whenever we get the invalid address, for example, invalid address or unsupported access, in that case slave error will be high. Okay, so that it indicate the failure, internal failure. So slave error is equal to 0 means successful transfer, slave error equal to 1 means error, some error has occurred. Okay, so that is what slave error. And before I told, right, P protect signal. Protect signal is nothing but where we have different these type of things. A protect signal to support both non-secure and secure transaction on APB protocol. Okay, just security purpose, or for hiding purpose or security purpose. Okay, so normally basic APB protocol 2.0 does not support the protect signal P protect. In AXI extension of APB protocol like APB 4, if you go to the APB 4 specification, I will share the specifications also. Okay, specifications will be very long. Same specifications we will take into the like these type of topics. Okay, but I will suggest everyone at least one time, at least 1 or 2 times read entire specification. Even for AXI also, AXI nearly 256 300 pages will be there. At least one time if you can read, you will get overall clarity in which version we have which features. Okay, suppose here APB we have P protect, but implementation wise we do in the APB4. APB4 is nothing but AXI. Okay, so if you read the specification entirely, then you will get the clarity. Okay, so it is just a protection control signal. Okay, whether it is a privileged, secure, non-secure data or instruction. Suppose if pre-protect is equal to 0 means data or instruction type. 0 means the data, 1 means instruction. Like that, P protect 1 means it's a privileged level. 0 means user, 1 means privileged, and 2 means 2 means secure. P protect of 2 means secure access. 0 means a secure, 1 means a non-secure. So here it is reversed. In some specifications we will have like this also. 0 means privileged, 1 means non-secure, secure, 2 means instruction data. It is interchangeable based on the design. Okay, so mostly where we use this P protect signal in the sense like in trust zone, mostly in trust zone, like whenever memory protection units are using, as I said, multiple number of test cases we are writing and we cannot send to the data to some, we cannot give the access. In that case, so we use this. Okay, just a second. Okay. So privilege access mostly we use in those type of cases. Okay. So mostly whenever you want to preserve some data, we use these protection attributes. And based on the it's a 3-bit size 2 down to 0, and to indicate this access we use the privilege mode. Okay, clear till here? Any doubts? No? Okay. So next, APB master. What is the difference between master and slave? What is the difference between master and slave?
Master is requester and a slave is respond to the request. It is a completer.
Okay. Any other answers? Others? Okay. So master is basically it's an initiator. Slave will respond to the master. Master will send the data to the slave, which is write data or write address. Slave will send the data to the master, which is a read data or read address. Okay. So APB master is nothing but there is a single bus master on the APB. There is no arbitration concept. Okay. If you see in I2C protocol, we have multiple number of masters. Because of multiple number of masters, we use the arbitration concept. Which master need to send the data first and which master need to send the data second. We use the arbitration concept. Okay. But here we have only one master. There is no need of arbitration. Okay. The master drives the address and write buses and also performs a combinatorial decode of the address to decide which p-select signal to activate. That means master will decide the slave because slaves are multiple. Based on the p-select signal, the master will select the one of the slave and also send the transfer, initiate the transfer to that particular slave. Okay. So it is also responsible for driving the enable signals to the time to the master, time to the transfer. So master is one of the responsible for driving the data. Whenever enable is high, it will send the data to the slave. Okay. It drives APB data onto the system bus during a read transfer. Okay. Next, this is what the whatever IC signals, whatever the you think it's a signals for APB master. Okay. So what are the signals out there? If you see system bus slave interface, this one system bus slave interface, that means master to slave interface, and read data. Read data in the sense before master. Suppose here master slave. Okay, so here master to the master, some data is getting. Okay, some data means suppose this slave is sending the data to the master. So this data will be the read data to the master, right? Maybe it is APB protocol or AHB protocol or even I2C protocol data or any simple component data, whatever. Suppose if it is serial communication here, that serial data need to transfer to the parallel because this master will accept only parallel data, right? So here the serial data should be converted to the parallel. That parallel data sending to the slave. Okay, so master is writing the data into the slave. Suppose if there are 3 number of slaves like this, slave 1, slave 2, slave 3, it will be selecting any one of the slave. Okay, based on that, the data will be transferred any one of the slave at a time, and then slave will get the data. Again slave need to transfer to the master, whether it is the same master or it's a different master. Slave to master means we call it as a read operation. Okay, master to slave means write operation. Slave to master means read operation. Okay, so that's why if you see here, system bus slave interface, from the another slave, master is getting the slave interface data and read data. Read data, reset, clock, common, and selector. Master should select any one of the slave, right? So P select 1, P select 2, P select N. Any one of the slave will be selected. Next, enable signal. P enable signal and address. Address and write. P address, P write, P write data. P write is equal to 1 means write transfer. If P write equal to 0, it's a read transfer. Okay. Clear till here? Any doubts?
Yes, yes.
What about remaining? No doubts, huh?
No, ma'am.
No, ma'am.
Okay, fine. Okay. So APB slave. Slave is very simple, flexible interface. The exact implementation of the interface will be dependent on the design style, and also having different options are possible. If these two signals are main, which mainly protect the lost data. Okay. While transfer of the data is taking place, there are P slave error and P ready signal. Okay. So if you see the slave signal here, slave input signals will be the P selector. P selector in the sense based on which slave has selected, that slave will accept the master data, right? Next, P enable. Whenever P enable is high, then only we can transfer the data, right? That's why P enable is high. And P address, nothing but which address, to which address we need to store the data. So P address. Next, P write signal. Okay. And P reset, P clock, both are same. Next, P write data. P write data and P read data. P read data is the read read data. So this is what master to slave communication. Okay. So APB master to APB slave communication. From remaining slave, the data is getting to the APB master and read data. So that data will be sent to the slave. That's what we call as a write operation. So P select P1, P2, which are used to select the slave, and P enable signal, P address, P write, and P write data, ready signal. Ready signal will be the outputs to the slave and inputs to the master, because P ready means P ready means wait signal. Wait signal in the sense whenever the slave is not ready to accept the data. Okay, suppose it is in before transfer, it is doing some other transfer, it is busy with some other data, some other transfer. In that case, the slave will not accept the next transfer. Okay, so that's why here the slave is telling to master, if P ready is high, the slave is telling to master to wait until P ready is low. So P ready is low means what it is indicating? It is ready to accept the data from the master. Whenever the slave is not ready to accept the data from the master, it will indicate P ready is equal to 1. Okay. Next, P slave error. P slave error in the sense slave should send the response, right? Nothing but response. So whether it is received the data correctly or not, it just indicate to the master based on the P slave error. If P slave error is high, write correct. If P slave error is 0, something wrong in the data. So this is what master to slave communication. Clear everyone?
Yes.
Any other doubts?
No, ma'am.
Hello, ma'am.
Okay.
Like how this P slave error will be generated?
What?
P slave error will be generated.
P slave error will be generated. We write in the design program. If what we write in the design program, suppose P master, P write data. P write data is equal to P read data. If both are equal, then P slave error is equal to 0 or 1, whatever the design you write. If P write data is not equal to P read data, then slave error is equal to high. Like that condition we can write. How we write the P ready signal? P ready signal in the sense, I will show you the waveform, you will understand. Okay, clear till here?
Yes.
Yes.
Okay, fine. So we have a simple finite state machine for APB protocol. For UART and I2C, we generated some finite state machine, right? Even for UART protocol, stop bit, start bit, and write data and parity bit. Based on that, we have designed one finite state machine. And coming to the operating for I2C protocol also, we have designed some FSM based on the start condition, address, acknowledgement signal, data signal, and not acknowledgement signal, and also stop condition. In the same way, APB protocol have very simple finite state machine. This FSM we can directly design. Okay, see here. 3 states, very simple. 3 states, ideal, setup, access, fixed. These names are fixed. Ideal, setup, access. Okay. So ideal statements no transfer. We don't do any transfer here, and that too P select is equal to 0, P enable is equal to 0. Both are 0, 0. Okay, in ideal state. Next, it going to the setup. Setup state. Setup state means P select is equal to 1, P enable equal to 0. By default, these are the values. Okay, according to these values only actual functionality will work. So setup means P select equal to 1, P enable equal to 0. Whenever this condition satisfied, then it will go to the access state, or else it will be in the same state only. We cannot do either write operation or read operation. Okay. Next one is access phase. Access phase means P select equal to 1, P enable equal to 1. Whenever P select equal to 1, P enable to 1, then only we can transfer the data, or else we can initiate the transfer. Okay. In the same case, we need to check with the P ready signal. So if P ready is equal to 1, then it is ready to accept the transfer. The slave is ready to accept the transfer. If P ready is equal to 0, it is not ready to accept the transfer. So we need to wait until P ready is equal to 1. So whenever P ready is equal to 1, then only it can access the transfer. Okay. So that is what. If P ready is equal to 1, no transfer, going to ideal state. Okay. So clear till here? Any doubts in the FSM?
No, ma'am.
No, ma'am.
Everyone, all.
No doubts, ma'am.
Yes, ma'am.
Sorry. Oh, sorry. Okay. Next, operating states. Whatever I explained, same. ideal setup, access phase. Now waveforms. So coming to the APB protocol, whatever the FSM we have written here, same FSM we can draw in terms of waveforms. Okay. So first waveform is write transfer with a no wait state. We have different 4 different types. Write transfer with no wait state means, if you see here, peak lock. Peak lock normally generated. So T0, T1, T2. Okay. T0 will be ideal phase. Ideal phase, setup phase, access phase. Ideal phase, setup phase, access phase. Okay, 3 clock cycles. If you remember first line here, in APB, every transfer take at least 2 clock cycles, setup and access phase, at least 2 clock cycles. Okay, so ideal phase, in ideal phase everything is 0, no operation, right? And coming to the FSM, just check in FSM. Setup phase. Setup phase is P select equal to 1, enable equal to 0. So here address is initiated from here. Write is high. Write is high means write transfer. P select is high. P select equal to 1, enable equal to 0. P select equal to 1, enable equal to 0. But still we can't transfer the data until we get this condition, access phase. So in access phase, we will get, in the third clock cycle, we will get select equal to 1, enable equal to 1. So in this phase, we can initiate the transfer. Okay, P select equal to 1, enable equal to 1. Now P write data, from here only it initiated the transfer, P write data. But can we write the data? No. Why? Because P ready is equal to 0 till here. P ready is equal to 1. So selection line is high, enable is high. When both are high, we can initiate the transfer. At the same time, P ready signal is also high. Whenever P ready signal is high, it is not indicating to wait. It is indicating you can transfer the data. Okay. So in this case, we can transfer the data at this particular cycle. Okay. Just check once again, observe the waveform and tell me if you have any doubts.
Like at T3 it will transfer the data. Hello? Hello?
Wait, I will come in 1 minute. Yeah, tell.
Hello, madam. At
Hello.
T3 it will transfer the data.
T3?
It will transfer the data.
Yes.
it will
In T3,
write the
here in T2 only we can transfer the data, because whenever select is high, enable is high, we can transfer the data. Suppose if it is a 8-bit data or 32-bit data, it takes some time. It takes a number of clock cycles. That's okay. But the transfer will be initiated from second cycle itself, T2.
okay.
Whenever both select and enable is high, the transfer will be initiated. Okay. Next, transfer with the wait states. So same example, but here,
One more doubt, okay?
yeah,
It
tell.
is the transaction will happen at
What?
cost to edge, right?
Your voice is low.
Actually, the transaction will happen at the cost to edge, right?
Positive edge.
Like at T2, okay, still the at the negative edge, okay, T enable and P ready
T2.
is at the T2, okay, at P
Hmm.
enable and P ready is low only. It will initiate the data transfer or it will initiate the data transfer at P3.
Which is low.
P enable and P ready.
P enable is 0, so we cannot initiate the transfer whenever both are high. Whenever P
Yes,
select
yes.
and P select and P enable, whenever both are high, then only we can initiate the transfer. If you see here,
Yes,
access phase. In access phase only we can make it both high. If you want to make it high at setup phase, you cannot do that. In setup phase, P select is equal to high, enable equal to 0. First of all, we are selecting the slave. So P select equal to 1. And then we are initiating the transfer. That's why in the next cycle, P enable is equal to 1. So that's what we mention in the waveform here. So here no wait state. No wait state means no need to wait for transfer. We can transfer the data. Okay. Any other doubts, others? Next, transfer with the wait state. Wait state in the sense overall same. Here it is the ideal state and P write is high. So P write high in the sense we can do the write operation. P select is high, but P enable is 0. We cannot initiate the transfer. Whenever P select is high, P enable is high, P write is high, and these three are high. But can we transfer the data here? Is it possible to transfer the data?
No, ma'am.
No. Why?
The slave is not ready to accept the data.
Okay, so because here P ready is 0. P ready is 0 means the slave is busy state. It is in busy state with some other operation or whatever. So it is indicating to wait. Okay, P ready is 0 means it just indicate as a wait. Whenever we need to wait until it is high. So whenever it is high, we can transfer the data. So at this point of time, in T4, the data transfer is happening. Okay.
Yeah.
Is it clear, everyone? So how can we write the program? How can we write the program?
And what is the difference between wait and without wait?
Difference between
Wait state without wait state.
Wait state, that's what I'm telling. If slave is busy, suppose first you have transferred 32-bit data. Okay. So slave is receiving this 32-bit data, and also slave is sending that 32-bit data to another master. Maybe slave is getting the data and also exchanging the data. Maybe two cases also possible, right? So whenever slave is sending the data to some other master, if you are trying to send some other data to the slave, will it accept? The slave will not accept here. Okay, so for that reason it is telling to wait until my task is complete. Okay, so whenever slave task is completed, p protect will become high. Okay, till then it will be in a 0 state only. It should complete its task. Okay, then only it can accept the next transfer. That's what it means. Okay.
Okay.
Next, so with the state with weight, with no weight completed. Now read side. Read side also same. But what is the difference for read side? Same waveform. Can you tell me what will be the difference?
Slave to master tool transfer.
Hmm?
Slave to master tool transfer.
Slave to master. Okay. In the same waveform, what we need to modify?
This period you have to
P write signal.
period.
P write signal. Okay. Then so P write signal will be low because it's a read operation. So P write should be low, and remaining all are same. P write is low, select is high, but enable is 0. Okay. At this point of time, the data is getting to read. We can read the data, but because of enable is 0 here. Because of that, we cannot read the data here. Okay. So we need to wait until P select is high, enable is high, then only we can read the data. In that case also, we need to check whether P ready is high or low. If P ready is low, at the same time, we cannot read the data. Whenever P ready is high, then only we can read the data. So here P select equal to 1, enable equal to 1, ready equal to 1. So that's why we can read the data here. Okay.
Like we can make enable and ready signal like T2
Uh,
before T2.
what? Speak loudly.
Like you can make P enable and P ready signal high before T2.
In T2.
Before T2 cycle. Like between T1 and T2 we can make high. P enable and P ready. We can
In T2, in T1, we cannot make enable as a high. So we need to
like
make it in T2 only.
okay, according to that FSM.
It is fixed. FSM is
Okay,
fixed.
fixed.
We cannot do like
Okay.
the first we are selecting. First we
Okay.
need to select and then enable. It is fixed.
Okay.
Okay. Next, no with wait state. So if you see here with wait state. So from T1 only the data is getting, but still we cannot read the data. Why? Because even P select is high, enable is high, but P ready is not high. So we need to wait until P ready is high. Maybe it is a 2 clock cycles or 3 clock cycles or 4 clock cycles, whatever. We need to wait until P ready is high, then only we can read the data. Okay. So this is with wait state. Next, failing write transfer. So failing transfer means it will be indicated with the slave error signal. Okay, slave error signal will be indicate the suppose here write operation. Suppose P select is high, enable is 0. Both P select and enable is high here. Data need to write, but still we can't write the data because P ready is low. Need to wait until P ready is high. So here P ready is high, and also data enable is high, select is high. So we can write data, but still here error is getting whatever we write the data, P slave error is high. So P slave error is high means it indicates the failure. It totally depends on your program. If it is a high, you can indicate the failure, or if it is a low, you can indicate the failure. Okay, this is for retransfer. Any doubts still here? Hello.
So we have only one master and one slave, is it?
Yeah. Hello, hi.
One master, one slave. Yeah, we can connect one
Like
master, one slave.
no arbitration concept in APB.
No, for masters only we have the arbitration concept. If there are n number of slaves, slaves can be accessed by masters. Master is transferring the data to slave. So slave doesn't need to fight for which bus need to run, which slave need to run the bus, like that. Those need to no need to fight. So always masters will be have the arbitration if there are multiple number of masters, but here master is one, slave is just getting the data from the master. Okay, that's it.
So we cannot have multiple masters in APB.
No, we don't have multiple masters.
Okay.
You may think like suppose one master, multiple number of slaves, master to slave, write operation or read operation, whatever. This slave will be connected to another master again. So now this will become the master. Like it is like considered as a single master. It doesn't depend on these three slaves. Okay, you may think like then these three will be the masters, right? No, these three are individual. So then in that case also one master to one slave connection, or one master to multiple slave connections.
Okay.
Okay, so these two will work as individual masters. Next, write followed by reader. That means write and read operations in a same. Okay, write address, read address. Mostly, we will store same. Write address must be same as a read address. So R and W. For write transfer, it should be 0. For read transfer, it is a high. So here we are writing the data and also reading the data, checking for ready signal, and here also checking for ready signal, error signal. Okay. By using these signals, how can we write the program? How can we write the FSM? And there are the disadvantages. You already know disadvantages are nothing but a single master, and we don't have the parallelism like pipeline operation, and low performance. Anyway, these are connecting with the low speed devices. So next, P slave error, and what are the advantages and disadvantages. So everyone understood the specification of APB protocol or have any doubts?
Ma'am, please explain the read and write transfer.
Read and write transfer. Here.
Yes, ma'am.
Yes, ma'am.
Okay, see here. Before example, we have taken just separately. So same here. Write operation means whenever write is high, address by default some address will be there, and whenever write is high, we need to check for p select is should be high, and select p enable is 0 in second clock cycle. In whenever p select is high and p enable is high, p ready is high, then only we can initiate the data transfer. In the same read also same. So whenever both here So write address, valid signal, just it indicates whether received proper data or not. So write is 0. So in this design, it just indicating whenever write is 0, write operation. Whenever write signal is high, read operation. Or else if you want to write whenever write is high, write operation, 0, read operation. Like that also we can mention. Okay. So write data. Here particularly clock cycles are not given, T1, T2, T3. Okay. But taking like read data, ready is 0 means we can't accept the data. Whenever ready is high, write operation can be done at this point of time. And whenever read signal is high, read operation, here ready signal is 0. So whenever ready is high, we can do the read operation. Here we need to add select signal and enable signal also. Whenever select is high, enable is high, then only we can write the data. Whenever select is high, enable is high, we can read the data. Okay. Any doubts still here?
No, ma'am.
Okay. So let me ask a few questions. So others, any doubts? Aditi, Amartya, Ashwini, Sai, Krishna, Gopinath, Himadri, Karthik, Manoj, Rajdeep, Shubham, Sweta, Srija, Venkatesh. Any doubts?
No, ma'am.
No, ma'am.
Everyone understood clearly? Specification?
Yes.
Okay, let me ask. Okay, so can you tell me what are the 3 different states for APB protocol?
Ideal
Ideal
setup,
state, access
setup
state.
state, and access state.
Ideal setup and access state. Okay, so let me ask one by one, line by. Okay, Aditi, can you explain the write transfer? What are the signals will be there and how the write transfer will be worked? Aditi.
Write transfer. Write data should be 1. Enable also 1. So
Whenever write is equal to 1, enable is equal to 1. Okay, remaining signals? What are the remaining signals? What are the remaining signals in APB protocol? Ashwini, can you tell me what are the signals available in APB?
We have P clock and P reset, P address, P write data, P write, P select, P enable, P ready, and PSLV error.
Okay. Next, Sai Krishna. Can you tell me what is the difference between P protect signal, P slave error, and P ready signal?
P ready indicates when the slave is ready to accept or initiate the transfer. P slave error indicates if there is any mismatch between the data which needs to be written or should be read. P prod indicates the protection level, like with the 2-bit combination, we have 4 combinations, which indicates the protection, like secured access, non-secured access, and stuff like that.
Okay, it's not 2-bit, it's 3-bit.
3-bit, okay.
Okay. Gopinath, can you tell what are those 3-bit protected signals P0, P1, P2, which will be accessed like privileged, non-privileged data instruct? Can you explain?
Yeah, mostly we'll use those 3, right? Like You want me to explain P of 0, 0, it's privileged or normal, like that?
Mm. Next, Himadri, can you tell what is the difference between APB, AHB, and AXI with the applications?
Yes, ma'am. APB is low power, non-pipeline, low bandwidth, which functions around 25 megahertz to 50 megahertz. AHB is medium to high performance with pipeline, high bandwidth, high performance bus, 100 megahertz to 50 megahertz. And AXI is high performance and have many channels. It is also pipeline and it is around 1 gigahertz.
Okay. Okay, good. Next, Karthik. Can you explain read with protect, read transfer with protect signal and be ready signal?
And for read transfer, read signal should be right, P right should be low,
Okay.
and there's P ready will be high, and one more signal.
Mm.
Three signals should be high for a read operation. One will be low, that is P right.
Okay, what about P ready signal and slave error?
Slave error, if any mismatch will occur, then slave error will high. Otherwise, it should low.
Okay, fine. Next, Manoj Kumar. Suppose a master initiate the transfer, okay, but slave never assert P ready. That means P ready is not high. Assert is nothing but assert in the sense, if you see here, this signal 0 to 1 transition, 0 to 1 transition. So it is asserting to high. That's what assert in the sense. Okay. So whenever master initiate the transfer, but slave never assert P ready signal, then what happens?
Unless period goes high, the transaction won't happen because the slave is busy with another data. Like, the transaction has not been completed, previous transaction.
Okay. So what happens in that case? I'm asking.
Like after the completion of present current data, then it goes to high. Then only the data will be, like, second transaction is going to be.
Okay, fine. So here, anyone talking? Okay. So here, what happens in the sense, suppose it is it is not asserting, like it is not high after 2 clock cycles or 3 clock cycles or 4 clock cycles, whatever, it is not high. Okay. So what happens in that case? It just indicate like a slave has stuck or design bug will be there or just failed, peripheral has failed. And also APB protocol is non-pipeline, right? So the master will be wait until P ready is high. But still, if it is not high, it will consider it as a timeout mechanism, will hang at the same point. Okay. So next question, Srija.
Yes, ma'am.
Suppose you have 3 number of slaves connected to the APB. two of them are accidentally respond to the same P select signal. Okay, so P select signal is 2, suppose, or P select signal is 1. Okay, so you have connected 3 slaves. 3 slaves in the sense, slave 1 should have 0, slave 2 should have 1, slave 3 should have 2, like that. Okay, but 2 slaves are responding by accidentally. So what will be the issue we'll be getting in this case?
Slave error.
Slave error. Okay. Suppose, okay, slave error is getting. In that case, can we have any solution for that where only one P select can access at a time? Can we, will be there any solution?
I think so. No, ma'am, it's a design.
In the design only, suppose if you use some decoder logic like that, is it possible? Okay, fine. Just work on that and let me know. Next, Venkatesh. I think everyone knows system Verilog, right?
Yes.
Suppose is responding to the P slave error signal. Okay, P slave error is equal to 1, so that it indicate the error. Okay, so as you are a verification engineer, how you will test this behavior? How can you test?
Like a peaceful is whether it's coming correct or not.
What? Speak loudly.
Like the testing means it's a peaceful is 1 or 0. You have to test.
Okay.
Actually, we compare this P-write data, P-read data.
You need to compare P-ready data, P-enable data. Okay.
The P-write data, P-read data.
Okay. So P-write data is equal to P-read data. If both are not same, P-slave error will be getting. Okay. So how can we verify in the sense whenever P-slave error is getting, it just about or in the log we need to get the test. Okay, fine. Okay. So next question for Aditi. Suppose master is writing the data to the slave, but no value is updating in the register. What might be the reason? Here, master is initiating the transfer and slave need to access the data. That means whatever the slave have some registers, it should store the data. It should update the data, right? But it's not doing that. What might be the reason?
Like the slave is already busy with some work, so maybe like master is not able to send it or sending the data but getting error like that.
Okay. Before we have seen valid signal, right? There is a valid signal. Valid signal is useful in these type of cases. Okay, so whenever the data is not valid, it doesn't update the registered data. Okay, so whenever valid is high, whenever it is not valid, we can check that it may be issue in the slave logic. So register is not unable to read the data properly or store the data properly. Okay, so next Suppose what happens if the master gives back-to-back transfers without waiting for P ready? Sai Krishna, can you actually it is not possible in APB. We can do in AXI because we have out of order transaction and multiple order transaction. But in APB protocol, what happens?
We might have a data loss,
Okay.
like without waiting for P ready signal. When the master is trying to send a data faster than the slave is processing it, we cannot capture that data.
So what modification we can do like to happen this condition?
We can check the ready signal for every transfer. Like the master should only send the next transfer once the slave signal is ready for by asserting the ready signal.
Okay. Can we write the assertions for that case?
Yeah.
Also, I will share some more questions of entire APB protocol. In tomorrow session, we will discuss RTL design and also system Verilog. And also we'll see how to design a test plan. How can we design our own test plan with the corner case scenarios? How can we cover? We can check tomorrow. Okay. Any other
Ma'am,
doubts today?
those questions are there in the PDF.
Yeah, I will share interview questions. Okay. Back-to-back transaction in the sense, suppose whenever we write the assertion in the sense assert P ready is equal to initiator. So that's what I told. Have some time.
Or only.
Okay. Okay, then thank you all. Bye. Good night.